Hello, my name is Fahimuddin.
Hello, my name is Luqmanul Hakim bin Zainuddin.
Hello, my name is Muhammad Aiman Hakim bin Azmi.
My name is Muhammad Aiman Hakim bin Azmi. So today I would like to present about what is computational fluid dynamics. Computational fluid dynamics, CFD, is the process of mathematically predicting physical fluid flow by solving the governing equation using computational power. For CFD, everything are done on a computer. It's also known as a process that produces quantitative prediction of fluid flow phenomena based on the conservation law. Modern engineers apply both, which is experimental and CFD. There are 6 processes of computational fluid dynamics. First, geometry and domain. Second, meshing. And next, boundary condition and fluid properties. Then, initial value discretization methods and solution algorithm. Next, solve iteratively. And the last one is post-processing. Before we go further, we need to know what is laminar flow. Laminar flow is infinitesimal parallel layers with no disruption between them. For laminar flow, fluid layer slides in parallel. And then type of flow is also referred to as a streamline flow. Regime is ruled by momentum diffusion. After we know about laminar flow, we need to know what is Reynolds number. Reynolds number is a dimensionless number expressing the ratio between inertial and viscous force, used to categorize the fluid system in which the effect of viscosity is important in controlling the velocity of the flow pattern of fluid. Reynolds number, named by Arnold Sommerfeld after Osborne Reynolds in 1908. On the slides show that numbers of Reynolds number for laminar flows and the formula of Reynolds number.
My name is Luqman. Next, I want to present about the objective of this project. First, learn how to set up the CFD simulation. Second, to find the laminar flow parallel over a flat plate by using CFD simulation. Third, to know the contour color difference from a flat surface. By knowing the color difference of each surface, we will know which part will facing the higher pressure. Last, learn how to achieve a high level of credibility and confidence in the result from the CFD performed. Next, we go to the relationship between CFD simulation and theory. At the side of the boundary layer thickness. In laminar flow, the boundary layer is typically thin and well defined. CFD simulation can be used to visualize and quantify the boundary layer thickness along the surface. Compare the simulated boundary layer thickness with the theoretical prediction based on the Reynolds number and flow condition. At the other side, which is velocity profile, laminar flows exhibit smooth parabolic velocity profile within the boundary layer. CFD simulations can provide velocity profiles at different locations near the surface. Laminar flow is characterized by well-defined parabolic velocity profiles. In CFD simulation, examine the velocity profiles at different cross-sections perpendicular to the flow direction. Next, I want to evaluate the effects of different airflow velocities on the profile of the boundary layer formed. First, I want to talk about the velocity profile. At 2 ms, the lower velocity of 2 ms, the boundary layer is more likely to be laminar. The velocity profile will exhibit a smoother and more gradual increase in velocity from zero at the surface to the free stream velocity. The flow is more ordered and predictable. At 2.5 ms, as the airflow velocity increased to 2.5 ms, there is a higher probability of the boundary layer transitioning from laminar to turbulent. The velocity profile in a turbulent boundary layer is more erratic with fluctuation in velocity. Turbulent boundary layers generally have steeper velocity gradients near the surface compared to laminar boundary layers. Second, I want to talk about the boundary layer thickness. At 2 ms, with a lower velocity, the boundary layer is likely to be thinner. The laminar boundary layer will have less mixing between adjacent layers, resulting in a more compact boundary layer. Next, at 2.5 ms, as the velocity increases to 2.5 ms, the boundary layer thickness is expected to increase. Turbulent boundary layers are characteristic by increased mixing and higher momentum transfer between layers, leading to a thicker boundary layer. Lastly, I want to talk about the explanation of effect. Laminar boundary layer at 2 ms. The flow is likely to remain laminar due to the lower velocity. Laminar boundary layers are characterized by smooth, parallel flow, resulting in a thinner boundary layer. Viscosity plays a significant role in the formation of laminar boundary layers. Potential transition to turbulent boundary layer at 2.5 ms. As the airflow velocity increases to 2.5 ms, there is a higher likelihood of the boundary layer transitioning to turbulent. The transition is influenced by factors such as Reynolds number and surface condition. Turbulent boundary layers exhibit greater mixing and momentum transfer, leading to a thicker boundary layer compared to the laminar flow.
Hello, my name is Fahimuddin. Next, I want to explain about simulation result. This velocity control plot. From the figure, we can see the temperature control level. The high temperature is warm and the lower temperature is blue. The line of plot is middle, so the coordinate for coordinate 1, 2.5 over 0 and coordinate 2, 2.5 over 1.0. Figure above represent the graph of residual over iteration. The left side velocity is 2.0 and the right side the velocity flow is 2.5. It represents three different lines, which are continuity line, x velocity and y velocity line. From the graph, we can see the residual decrease while iteration increase until steady flow. And the last one is charge viewer velocity u over y. This charge based on the color code of contour, and we can see the value velocity 2.5 more than velocity 2.0. That's all. Thank you.
In this workbench, let's have 5 steps. The first one is geometry. The second one is mesh. The one is setup. The fourth is solution, and the fifth is result. I want to explain part by part in this video. Okay, the first one, I want to proceed in geometry part. Okay, now I want to set up the dimension. Where the question given, V1 is 1 meter and H2 is 0.5 meter. And I want to set up the dimension and the shape at geometry part. And now set up the grid line and then draw a rectangle. After that, I want to set up dimension while V1 and V2 is the same dimension. That is 1 meter and H1 and H2 is 0.5 meter. I change the dimension 0.5 meter and 1 meter. And then I apply base object and generate it. That's all for geometry part. The second part is mesh or meshing. Okay, the first one I want to create the Z-axis to be 2D. And then need to generate mesh because it not have the characteristic. And then I click mesh and click the face meshing, and I select the face on this shape, and we can see after generate mesh, we can see the grid line is straight. And then I click a sizing at the mesh. This is for contour number of grid point each boundary. The scale factor for a selected body, face or edge. The mesh is used to get accurate on the simulation. Then I use number of division is 50, and the behavior I change from smooth to hard. After that, I click the left side, and number of division is 50. And base step, I use base factor, and I set up the value is 70. And the same step, I change the behavior from smooth to hard, and I generate it. After that, I do the same thing at the right, and I set up the number of division is 16, the base factor is 70, and the behavior I change to hard. And then in this step, in this side, I click a reverse base. Reverse base for the shape is parallel from to the big, from the big to the small. It's parallel from the other side. That's it, the left side. And after that, I assign name. I use icon surface, and I right click and create name selection, and I tap a airflow for this selection, and then I click airflow, and I select icon edge, and I select and set up for the left boundary. For the left boundary, I set up the name is inlet, and the right is outlet. Top and bottom, I set up the name is fluffy pressure for the top and plate for the bottom, and then save it. That's all for part mesh. Okay, the step is for setup. I click double position for more accuracy, and the process I choose one. At the setup part, at the model, I change from viscous to laminar, and the material I click air, and I change the density to 1, and the viscosity I change 1 exponent -4, and change, and I close. And then at the boundary layer condition, I click inlet, and I change the velocity magnitude to 2 from the question. For my group, get the value 2 and 2.5. From this video, I want to show at velocity 2, and I click outlet. I set up 0 for gas pressure. This means it's for atmosphere condition, and for field, I change to symmetry. After that, we continue the next part. That's it. So the same part. And the first step, go to method and change scheme to simple. and then go to monitor and click residual and change the criteria to 1 exponent negative depth to get a steady flow, and then click to initialize, click inlet and change its velocity to value of 2, and click on calculation and change number of iteration to 700. Number of iteration, the number of the time per specific operation or process is repeated. I use 700, and the limit for the chart is 700 only, and we can see the flow is steady after average 400 and above. That's all for this part, and we continue for the next part. Final part is result. Click to the axis to get 2D, and then click the counter icon and click OK, and change location to 72, and change variable to velocity, and now number of counter I change to 50. Number of counter to see variation of color beam, and I click apply, and you can see that the T-max on the near the plate, and then I click chart, and I change x-axis to velocity u for variable, and y-axis variable is y, and click apply, and then I click the contour one and use the location and plot, and I click the insert location and line, I click OK, and then I plot a line. My value is 0.5 for x, and y is 1, and I divide by 2, 0.25, 0.5 and 0.1, and I change the sample to 100 and I apply it. After that, we go to series 1 on the chart, and the location we select the line 1 and apply it, and we can see the chart of value or velocity 2.0. After that, we add the series 2, visit the value of velocity 2.5 and apply it, and we can see the difference between chart velocity 2